Hello, good morning. My name is Ashutosh Garg, and today we are going to be doing the stack and draft calculations as a part of our fired heater design webinars. Just to give you a little background, about 2 years ago, I thought that I should publish or all about my work, all the fired heater designs that I have been doing. And a number of times I thought about even writing a book. But then I realized that the times have changed and it is a lot more effective to have videos and put them on YouTube. So 2 years ago, I devised this 12-part design program or webinars, out of which we have done 6. My original plan was to do once a month, but as you know, life is not perfect, so we keep on having breaks. But now I think I am determined that we do the rest of the 6 sessions in the next 5 to 6 months, once every month. So that's a background, and we are going to be talking about stacks, design, and fired draft control. In the earlier webinars, we covered the basics of fired heater design, what information is needed for designing fired heaters. Then we did combustion calculations, because combustion is very much integral part of fired heater design. We are burning fuel gases or fuel oil to generate heat and then transfer them into the process. Then we covered the radiant section, and radiant section is very important section, or it's basically, you can call it the main part of the heater, where 70% of the heat is transferred in the radiant section. So we covered the design of the radiant section, and we did 2 webinars on radiant section because radiant cannot be covered in one. And then last time we did convection section, because convection section is also an important part of fired heaters. So all these 6 webinars are available on YouTube now. If anybody wants to go through them, he or she is more than welcome to check them on YouTube on our Furnace Improvements channel. And today we will cover about stacks. And you may ask me, why are we doing stacks and dampers? Because stack is a very important component in the fired heater. Stacks typically have dampers, and damper control is 50% of the control in the field. When there are operators in field operating fired heaters, they are mostly adjusting 2 things: burner registers and stack dampers on a daily basis. So from that point of view, stacks are important. Stacks have become important in the past 50 years because of pollution, because of ground level concentration of NOx and SOx. Stacks have become important. Prior to that, stacks were mostly designed for creating draft. But in the last 50 years, the function has changed, and we are looking at not only safe disposal of flue gases, we are also looking at ground level concentration of pollutions like NOx, SOx, and all those particles. So let's start talking about stacks. Just to give you a brief background about myself, I'm hoping most of you know me, but again, my name is Ashutosh Garg. I'm a chemical engineer. I passed out more than 50 years ago from IIT Kanpur in chemical engineering. And I have been very fortunate that out of 50 years, 48 years have been spent with fired heaters. The first 2 years, I was working in an ammonia plant, even though there were steam reformers and other fired heaters. But once I moved to KTI Corporation back in 1976, I've been working on fired heaters. For the last 28 years, I've been working with furnace improvements, and our company specializes in revamping of fired heaters. We also supply new fired heaters, but our focus has been uh, revamping of fired heaters, and I will tell you a little bit about that. I also have been very fortunate to have very good bosses and mentors throughout my career. Whether I was working in KTI, Engineers India, KTI Corporation, uh, I have been very fortunate that people taught me a lot of things which I have been able to expand in my last 24 years, 25 years. So, with that background, I want to tell a little bit about furnace improvements as they are the ones who are footing the bill for this webinar. Uh, we started in 1996. We have been in business for more than 28 years. Our main office used to be in Sugar Land, Texas, but for the last 5 years, our main office has moved to Noida, which we opened in 2005. That is our main engineering office. And Sugarland office is mostly sales and project execution office to take care of the existing projects. Uh, One of the salient features of furnace improvements and in my career has been the contrarian approach to works, to my projects. And as a result of the contrarian approach, trying new things, we were able to develop three new technologies in the past 20-25 years. We have three patents, we have a split flow technology, we have inclined firing technology, and we also have a smart damper technology, and I will tell you a little bit briefly in this webinar. And these technologies have been developed again based on the needs of the client. Our model, the way we work, our model is working directly with end users, refineries, petrochemical plants. That's how we have been working. And our mission is to improve the performance of existing fired heaters. Our motto is do it once, do it right. And we are able to work round the clock because we have two offices and because of the 11-hour time difference, 10-hour time difference, we practically are able to work round the clock. So if you have not worked with us, I request you to try us out, challenge us with your project. If you are a refinery, if you're a petrochemical plant, give us the worst heater, the heater which is giving you the most problems, and we promise that we will make it the best heater. That's what our promise is. We have done it several times and we can do it again for you. We work on all types of heaters, reformer heater, crude heaters, hydrotreater heaters, coker heaters, CO boilers, SCR units, ultra low NOx burners. So our range is all, including steam methane reformers. This is the list of our clients. Most of our work is US based, but we have done some work in Middle East, Europe, India. So that's pretty much the list of our clients, what we have in the last 25 years. These are our engineering capabilities. We are just like any other fired heater vendor. We can do design, engineering, fabrication, erection, the whole turnkey basis. We can do it. We have done projects. We have FRNC5, we have START, we have AutoCAD, we have SolidWorks for 3D modeling. So we have all the softwares with us. This is our patented technologies. I won't take much time now, but you can find webinars on these technologies again on YouTube. Uh, if you are having pressure drop limitation, if you are having flame impingement in your fired heaters, if you are having high tube metal temperatures, coking issues, we can help you solve it at a very, very uh, low price, just using diagnose the problem. If you are having high excess O2 issues, our smart stack damper can help you. All right, now let's get back to the technical stuff or go back to the fired heaters. Fired heaters are one of the most important equipment in the refinery. Any refinery can have uh, from anywhere 20 to 60 fired heaters. You know, they are major energy consumers, and most of the fired heaters will have three sections: radiant, convection, and stack. We burn mostly fuel gas these days, but there are still some clients who burn fuel oil, and they burn it with combustion air to generate heat, and that heat is transferred to the process to preheat the charge, whether it's for the crude service, vacuum service. And the flue gases, which are products of combustion, are vented to the atmosphere through the stack. That's basically how the fire heater construction is. I'm sure you all know that. So three functions of stack, as I said in the beginning: safe disposal of flue gases and controlling emissions. The most important function of stack is to create a negative pressure inside the fired heater. Fired heaters are very different as compared to boilers. Most of the technology in fired heaters came from boilers because boilers has been there for I think 400 years now. So, but fired heaters are process equipment, and being a process equipment, we want them to be inherently safe. And because of that reason, we want to make sure that anytime anybody opens any peep door, the flue gases should not come out. So we keep negative pressure inside the firebox, inside the combustion chamber, inside the convection section, everywhere. So stacks, the main function is to create negative pressure in natural draft heaters. There are heaters like steam methane reformers, ethylene cracking furnaces, where the convection section is very large and the efficiency is very slow, uh, very high, sorry, efficiency is very high, flue gas temperature is very low. So in those cases, we use induced draft fans to create draft. But in natural draft heaters, we use stacks to create negative draft in this thing. And that's what we will cover today in our webinar. There are different types of stacks. I just want to show you some pictures. Most common is convection mounted. That means mounted on top of the convection. There are grade mounted stacks, as you can see in this picture. And grade mounted stacks typically are for multiple heaters. Common stack for multiple heaters. This is another configuration where we have a convection top mounted stack, but there are 4 small heaters tied to the main stack. So that's another configuration for stacks. So the stacks, the main function is to create negative draft, and the industry, what industry has settled on, the draft number is zero point 0.1 inch or 2.54 millimeter of H2O. That's a minimum draft you want to keep at the arch. Why arch? Because arch has the highest pressure. So if you make arch negative, the whole heater will become negative automatically. That is how the fired heaters are designed. So you don't need to control pressure at 10 different points. You just control pressure at arch, and if you make that negative, automatically the whole fired heater will be negative. Let's talk about pollution considerations. So we want to have minimum height for dispersion and safety. And here you will see very different standards in different parts of the world. In US, the typical standard is 100 feet or 30 meters in US. And that has been because of clean burning. In US, most of the heaters are burning clean natural gas. And because of that reason, uh, 30 meters was deemed sufficient. In India, typical stack height requirements have been 60 meters or 200 feet. And the reason is because for a long time they had been burning fuel, not only fuel gas, but fuel oil, and fuel oil with high sulfur. So once you have sulfur, then the ground level concentration of SO2 and SO3 kicks in, and that's one reason uh, stacks have been 60-meter tall. There has been change in India also. I think they are getting a lot of LNG, and most of the heaters are working on natural gas. So things may change again, but that's typically. And in Europe, it was altogether a very different design philosophy. In Europe, the space are very limited. So the refineries were very close to the people living. There was the distance between the refineries and the residential colonies or cities was very small. So the ground level concentration needed almost 100-meter stack. And a 100-meter stack is very expensive or very large. So what they did was they connected 20 heaters to a single stack, or 10 heaters to a single stack, or 30 heaters to a single stack. And these stacks were made out of concrete with an elevator and everything. Uh, but I think Europe also, they are trying to change to gas firing, and hopefully maybe the philosophy may change, but these are typically the current pollution considerations. Another consideration which a lot of people follow is the stack tip should be 15 feet above the tallest platform. That is just to make sure that the operator never gets to touch the plume, the hot plume from the flue gases. The picture below shows that the effective stack height not takes into account not only the actual height, but because of the buoyancy, there is an delta H which is created, because of the velocity. So that adds to the height or gives the benefit. Typical guidelines: if your stack is less than 100 feet tall, you can mount it on top of convection. If you have a more than 100-foot tall stack, you may go for grade mounted. This is just a guideline. It doesn't have to be. Uh, it changes from case to case. So you can have a 150-foot stack on top of the furnace. That's fine. Or you can have a 100-foot grade mounted stack, depending on your situation. We can do the stack in three different common configurations, and this is mostly left to the structural engineers. Structural engineers, they come up with the most economical design of the stack. So the most common is a straight stack, all the way, and then you have a stack tip on the top. Little less common is the conical stack, even though we do it, uh, where the 1/3 of the stack length is conical, and then you have a straight portion. And the third is telescopic stack, and that is like making the stack in three sections. Telescopic stack is mostly used where you don't have very high capacity, but you have very tall stack height requirements. Let's say you are putting a heater which is maybe 50 million BTU, but you want to have a 150-foot or 200-foot stack. So in those cases, telescopic stack can be very, very useful. But talk to your structural engineer and he will typically come out with the most important. So as I said, the stacks are mounted on top of the convection section. But how they are mounted is important. And that's where breeching comes in. Breeching is kind of a component which connects the stack to the convection section. And generally, we provide about 750 millimeter or 2.5 feet space for collecting the flue gases. And also, you want to have a gradual contraction. You don't want a sudden contraction. So you want to provide 15-degree angle. And every 35 foot, depending on the convection section tube length, if your convection section is 60 foot long, maybe you have to provide two offtakes. And general recommendation is that these offtake velocities should be low, around 15 to 20 feet per second. That's the general guideline, although you will need to do exact draft calculations. So this is a typical guideline, or good engineering practice which you want to follow. In fired heaters, we normally provide refractory lining. And the purpose of refractory lining is to protect the metal against high temperature. That's the most important. Reduce heat losses, avoid any flue gas dew point condensation and corrosion. That's typically. For most of the heaters, we use 2-inch thick LH14 mix. And for heaters which are all radiant, you provide 3-inch thick lining. Unlined stacks are not recommended, even though for a little while API 560 allowed unlined stacks with a flue gas temperature in the range of 400 to 700 degrees. To me, that is cutting corners. So we don't recommend it. Also, we don't typically use externally insulated stacks. You can do it actually, and they are very popular in boilers. You will always see externally insulated stacks, but in fired heaters, we mostly stick with the refractory lining on the inside. Let's go get into a little bit of designing now. What velocity should I use for sizing stacks? Uh, General guidelines for natural draft is 20 to 30 feet per second or 6 to 9 meters per second. Minimum velocity, you can go down to about 3 meters per second. And typically for the tip, you may want to keep high velocity. I would recommend anywhere between 30 to 40 feet per second to make sure that you don't get into any inversion issues even at the low uh, capacities, But it's all depending on how the heater is going to be operated. If you have a stack with an ID fan, that means there we normally use about 50 feet per second or 15 meters per second as the velocity. I forgot to tell you that if you have any questions on this webinar or any of my webinars, you are more than free to send me an email at info@heatflux.com or agarg@heatflux.com, and I'll be more than happy to answer your queries. I'm not very high technically savvy actually, even though I try to do a lot of things but I'm not very good opening the chat box here and getting your questions and then answering them. So I see if there is some uh, this thing. Let me see what these are. Okay, so these are joining issues, so I can't help you, but maybe we will. Yeah. So that's where the stack guide velocity guidelines are there. As I said, exit velocity is very important. You want to keep as high as possible. You can make stainless steel stack tips, and if you have a high tip velocity, it will give you better dispersion or more uh, lower ground level concentration, of the pollutants. So when it comes to the stack diameter, it depends on several things. Convection section pressure draft, how much is draft available, what is the flue gas velocity we have used. If we have an induced draft stack, then it's more about structural stability and flue gas velocity. Uh, but natural draft stacks are a lot more critical on velocity and draft availability. So just for the benefit of maybe mechanical engineers who are attending this webinar or people who are not very familiar with fired heaters, uh, what is furnace draft? So just to give you a quick this thing, inside the furnace we have hot flue gases, and outside the furnace we have cold ambient air. And because of the density difference between the flue gases and ambient air, a driving force is created, and that driving force is used for supplying combustion air to the burners. So you can see the people who designed fired heaters or who conceived fired heaters were very smart people, and by keeping negative pressure inside the furnace, they were able to achieve two things. They were able to eliminate the need for an FD fan, and they were able to make the heater inherently safe. That's how they were able to do it. So let's talk about what is furnace draft. Atmospheric pressure 14.7. Before I finish, I forgot. I'm an old man now in 70s, so I forget a lot of things. I want to thank my team of process engineers in Noida office who have been helping me and working on these presentations. I have a very good team and they do a fantastic job. I'm just the messenger here. I don't do any hard work anymore. So those people, my process team, the drafting team, they have done an excellent job. And they have put this presentation. They sent me this presentation this morning and said, okay, you are ready to go. So thanks to all my team members. And they have done this job. So atmospheric pressure depends on the site altitude. 14.7 psi is at zero elevation or sea level as we call it. And at sea level, anything lower than 14.7 is known as negative pressure. And the difference is known as draft. In US, we measure the draft in inches of water column. In outside US, we measure the draft in millimeter of water column. I know there are so many people from Europe and India attending my webinar, but I've been so accustomed to the British units, it's very hard for me uh, to get down to both the units. My brain does not work with the metric units anymore, because of the last 30 years or 35 years of working in US. I'm accustomed to or tuned to British units. So induced draft fans, a fan is doing the function, so the stack dimensions or stack design is important, but it is more important from just the velocity, vibration, structural stability. Those are the issues. Whereas in the natural draft heater, the function is to provide the draft. The stack should be able to create enough draft so that we can have combustion air coming into the furnace. So as I said, where do we measure the draft? And the way heaters are designed, you should measure the draft at the arch. And arch is the section which is radiant outlet or convection inlet. That's basically, we call it arch. And that's where when we are designing fired heaters, we are keeping the pressure at the highest over there, around 0.1 inch. And draft is very easy to measure. You can measure it using a portable draft gauge. You can measure it using a water manometer. And our recommendation is to put at least 4 draft gauges on the fired heaters, at the heater floor, arch, upstream and downstream of the stack damper. That's typically the 4 recommendations what we want to do. Typical arch values, I think we have been repeating this, but typically 0.1 to 0.25 inch is what is used for convection section inlet. Heater floor, where the most of the time burners are located, will have about half inches to 0.7 inches. It depends on the height of the radiant section. Every 10 feet of radiant section height will add about 0.1 inch water column. So why are we talking so much about draft control? And the reason is there are two important parameters in fired heater. One is draft, other is excess oxygen. Both are equally important. But what has happened in the industry is that oxygen analyzer became the darling of all the process engineers, instrument engineers, all the companies, because oxygen analyzers are very expensive. Companies make a lot of money. So oxygen analyzer got the good treatment. I don't have the word to give it. But the draft became like a step brother of oxygen or step sister, and nobody took care of the draft because draft meter cost only $100. So maybe there was not too much money to be made. And as a result, what has happened is we have been doing surveys of fire heaters for last 30 years. And we find draft is the most neglected parameter in fired heaters. I go to the refineries, I talk to process engineers, mechanical engineers, and they only talk about excess oxygen in their furnace. They are only focused on excess O2 in their fired heaters. But when I ask them about the draft, they have no clue actually. Absolutely no clue what is draft and where is a draft meter and what should we be keeping actually. You know, so that is why we are talking of draft control over here. And I would say part of the time that it's the fire heater industry which is to be blamed. Most of the fire heater industry treats stack damper as a plate on a rod. And nobody thinks of stack damper as a control valve. Whereas it is a control valve. It is a final control element. I mean, if you ask anybody, any instrument engineer, it's basically it's a, but it is not given that treatment. And as a result, most dampers do not operate correctly. And it is to be because of the quality, design deficiency, quality. And we keep on blaming the operators all the time. We should be blaming the engineers here. The engineers who designed those dampers, engineers who engineered those dampers, they should be blamed. Because the amount of air induced in a furnace is depending on the draft. And amount of air means excess air. If you have higher draft, you will have higher excess air. If you have no draft, that means no supply of air. So draft is very, very important parameter which we need to control. And again, it is directly related to the Tramp air leakage. If you got high draft in your furnace, you will have more leakage. And air leakage messes up your O2 analyzer, leads to after combustion, because O2 analyzer cannot differentiate between the two airs, whether it is coming from the burners or whether it is coming from the peep doors or leakage. So if you want to minimize Tramp air leakage, you need to understand the importance of draft. And this is a simple table. You can even find it, I think, in APFI 60 if you are familiar. If your oxygen level is high and draft is high, you need to close the stack damper. And closing the stack damper will have following effects: reduced O2, decrease draft, firebox temperature will go up, stack temperature will go down, your heater will be more efficient. So all these things will happen. Let's turn to a little bit of calculations. Uh, I don't want to scare you with the calculations, but very simple calculations we have talked about here, and you can calculate the stack effect using very simple formula. Uh, we're given over here, which is molecular weight of air and molecular weight of flue gas, almost identical. Air pressure, flue gas pressure, air temperature in degree Rankine, and flue gas temperature in degree Rankine. So stack effect depends on the summer ambient temperature. And if you're doing a project in Middle East, make sure you take the maximum temperature over there, which could be 120 degrees. Stack effect also depends on the altitude of the site. And it happened with me. Actually, I was very new to US. I had just come in 1990. I was doing a PMEX project. They had two projects and they were supposed to be identical. Uh, but what people did not realize was one site, Tula, was at 6,000 feet elevation, 2,000 meters above the sea level, and the other site was at sea level. So how can the two be the same heaters? You cannot have the same heaters even though the duty and everything is identical. It will not be the same. It will have to be different. So make sure you understand the importance of elevation. As this is a formula for elevation, that if you're 100 feet of elevation, your draft will, the atmospheric pressure will go down by 1.47-inch water column. And these are typical draft numbers. At 1400 degrees, you generate about 0.1 inch every 10 feet. At 400 degrees, you generate 0.6 for every 100 feet. At 700 is 0.8. So, but you can calculate these days very easily on Excel or any other program. These are a few formulas again for stack calculations. We normally do stack calculations using velocity heads. And velocity head is defined as density of the flue gas and the velocity of the flue gas. And the formula we use is 0.003. You can neglect all this, just use 0.003 rho v square. That gives us, rho is in pounds per cubic feet, v is in feet per second. That will give you in inches of water column. Similarly, you can calculate stack friction loss. You can calculate stack exit loss, which is one velocity head. Entrance loss is half velocity head. And damper losses we take is about 1.5 about rho v square. That's the damper loss we calculate. Other losses, contraction and expansion, and my team has given you all these coefficients and units, so they can be helpful to you. And this is the draft profile inside the fired heater. As we said, this is a point or arch which has the highest pressure. So this is typically how the draft profile. This is the draft profile at the floor and at the burners. Then convection section, damper, and stack. So stack sizing calculations. We are given you 7 steps over here, and typically use 0.1 inch draft at the arch. That's a starting point. Then you select the stack diameter, calculate the stack height, and that's basically it. And then show it to your structural engineer and ask him whether this stack is good or bad. So we do have a case here. I want to show it to you. We have a case which is for a real project. The design heat duty is about 91 million BTUs. This heater was burning fuel gas and fuel oil. Efficiency is about 86%. Flue gas temperature leaving is about 540 degrees. My team has already given you the answer over here. A top mounted stack, 8-foot diameter. This thing, flue gas velocity, we selected 18 feet per second. But here is the ambient temperature what we have used. Flue gas flow rate. Typical stack design will have about 20% margin on the flue gases. Came up with a diameter of 8.5. Stack velocity 18. And this is a hit and trial method, This is not like a one-shot method. You keep on looking at different options. You calculate the total stack effect, stack losses and convection losses, and then you get the total flue gas pressure drop 0.4534, draft zero point 0.1. So it's kind of this adds up to over here, And this is the losses. Stack height required is about 70 feet. They have done a design. This is, I think, what we have selected. This is a design with higher velocities, and this becomes structurally unstable. And this one would have been a good design, but we had the height restriction. We could not have gone above 150 feet. So we had to select this design and not this design, But that's typically stack design is pretty straightforward design. This is what as they have given you over here. We can go 18 feet, 25 feet, 30 feet. All of these will be workable. H by D is 8, 13, 18.6. Still up to 20 is allowed. But here we had to keep the stack height no more than 150 feet to use the existing foundations. So because of that reason, we had to select this value. But pretty straightforward calculations, not something very difficult. Conventional dampers, there are two types of dampers we use in the industry, parallel blade or opposed blades. Mostly this is the linkage, and all damper blades move at the same same angle. This is opposed blade, this is parallel blade. They have been used in the industry for last 50, 60 years now. I hope all of you are familiar with API 560. If you have not read API 560, API 560 is the Bible for fired heaters. It's an excellent document which has been compiled by American Petroleum Institute. American Petroleum Institute constitutes of all the oil refining companies in US, worldwide, all the engineering companies, all the heater vendors, they get together twice a year and come up with these excellent specifications. So if you're not familiar with API 560, my suggestion would be to read API 560. Here are some points my team has put from API 560 recommendations for stack design. Damper design temperature shall be 200 degrees higher than the maximum flue gas operating temperature. Maybe damper assembly shall be operated at a minimum temperature of minus 20 degree F. Recommendations for carbon steel. Although most people go with a stainless steel damper, I have never seen a carbon steel damper, And APS 560 says every 13 square foot of area will need a blade. So if your stack has 50 square foot area, then we need 4 blades. And they also put a maximum blade width limit of 30 inches for operations reason. So if you follow these guidelines, you will come up with a pretty nice stack damper. This is the pictures of a stack damper here. Uh, Most of that stack dampers or stacks are oversized, and if you're looking at a control valve, it's a full size control valve, whereas in the reality you need a reduced port area. So API 560 recognized this problem, and now they have come up with this new recommendations. Damper position should not be less than 20%, no more than 70%. So these have been recognized now, but we have been working on this problem for last 10-15 years now. We understood that the stack dampers are highly oversized and they create very high draft. So we came up with a smart damper. So we have done a lot of research. All this is all there. And we realized that because of the margins, stack dampers need to be properly engineered. And we have this design. So this is our patented design, a 4-blade design where 2 blades are kept closed and 2 blades are open, and they are operating. So that gives the flexibility to the operator to get the best control and also not to lose the flexibilities. In case he wants, he can always operate all the 4 dampers, and we achieve it very quickly, very simply by instead of putting one actuator, we put 2 actuators, and that's all what we do it. And by doing this, we are able to change the CV of the control valve. We treat stack damper as a control valve. So this is our smart stack damper. We have supplied recently 3 units in Europe. We provide smart stack dampers as a standard equipment for all our new fired heaters. And you can see this was the stack, very unusual stack having an inner circle and an outer circle. And we put 4-blade damper with 2 actuators to ensure that we can get the best control. These, these heaters were suffering from high excess O2 issues like 8% O2, 10% O2, and we are trying to control. We have also supplied a similar damper to a company in Israel. And if you have a stack damper, we can convert it into a smart stack damper at a very, very low cost. All right, guys, thank you very much. I really appreciate your time. If you have any questions, you are more than welcome to send me in a chat box. If you like, we still have about 7 minutes. I will be able to see them and answer your queries. I'll wait for a few minutes here. So one of my old friends has a question on rain hats on stacks. Rain hats on stacks are not very common. You know, you can do it. It only adds a little bit more pressure drop on the stack. So the stack height will go up if you put a rain hat. Most of the time, if your heater is operating and if it's still raining, that rain will get vaporized. So uh, I may not be able to give it to you, the delta P, you will have to calculate it. I don't have it handy with me, but you can calculate. I don't have it handy, Santanam. Yeah, but anybody else has any questions? Please feel free to give me an honest feedback how we can improve our webinars, how you know we can make them more effective, and hopefully I will have a next one on air preheaters next month. So we are thinking of doing one webinar every month, and so that we can complete this 12 parts, and then I think maybe I will have some few more webinars on the projects what we have done. Okay, if nobody has any questions, I will try to close my webinar. Thank you again very much for joining and listening to me, giving me a patient hearing. Uh, and we look forward to seeing you again. Keep connected. Thank you, guys. I see familiar names. I I wanted to share something with you. I should have told you actually that in 1980s, 1985 or 1990, I mean, I realized that fire heater design was very closely held by a few people, or there would be one person in each company who would have all the fire heater design in their heads. And I think I feel very good about training at least about, I would say about 50 engineers, if not more, during my 50 years. And hope they can all carry on, when I'm not there. So it's been a really good innings which I've had, with all the guys. Thank you.